Fatty acids are very long-chain carboxylic acids in living systems used for energy storage, and they're an important source of energy storage because of the relative stability of the carbon-carbon bonds in these compounds. So an example of a fatty acid ester might look something like this, with a lot of carbon-carbon bonds in the structure. A fatty acid would have a carboxyl group here, CO2H. These are also found in esters. Triglycerides are the most famous and important examples where three fatty acids are linked through glycerol in a triester structure. And fatty acids, immediately kind of bring up the question, how in the world do we make all of these carbon-carbon bonds, right? These just look like plain vanilla CH2s, and it seems difficult with no functional groups there to actually form these bonds, especially in living systems where things like carbanions and alkyl halides are generally not seen. The answer here is that each of these bonds, the alternating carbon-carbon bonds, are formed via Claisen condensation involving two carbon units. So two carbons are added at a time, and each of these bonds in purple is actually made through a Claisen condensation, as we'll see. So in the remainder of this video, we're going to dig into the mechanism of biochemical Claisen condensation and fatty acid biosynthesis. What I hope you'll see is that fundamental organic chemistry is a very useful lens to view these biochemical transformations. You don't want to approach it from the model of memorizing what the reactants and products are and what the metabolites are, what the enzyme names are, that kind of thing. Approaching this from the lens of fundamental organic chemistry will help you see why and how these reactions take place. For example, malonyl coenzyme A is nature's Claisen nucleophile, and this is malonyl coenzyme A. It resembles malonic acid, which would have two carboxyl groups. Here we have a carboxylate. This is the predominant ionization state of a carboxylic acid under physiological pH conditions, and a thioester over here. And unlike the laboratory Claisen condensation, this Claisen condensation is going to involve thioesters rather than esters. However, the basic chemistry, the electron flow here, is highly analogous to what we've already seen for these laboratory Claisen condensations. And we can form malonyl coenzyme A, and it is formed via carboxylation of acetyl coenzyme A, which is this structure on the left. I should also add that the coenzyme A group is a very large organic cofactor that we don't really need to worry about. It's pretty much purely used for molecular recognition in this context. The actual reactivity occurs in the acetyl group or the malonyl group, as we'll see. So this carbon between the two carbonyl groups is going to act as our nucleophile, and that should seem familiar from previous discussions of the, for example, malonic ester synthesis, where a very similar carbon was deprotonated by alkoxide base and we alkylated it. Both of these coenzyme A thioesters bind to acyl carrier proteins before the reaction takes place. We're going to abbreviate those as ACP, and then the actual bond-forming event occurs inside the active site of an enzyme. So here I've just linked up the malonyl group to the ACP and the acetyl group to the ACP. And in the ensuing bond formation, this carbon will be the nucleophile via an enol or enolate, probably an enol under biochemical conditions. And this carbon, an acetyl coenzyme A, will be the electrophile. So something to notice here is that CO2 is given off. This carboxylate group is actually lost. And we end up with this beta keto ester looking structure, or 1,3-dicarbonyl structure more generally, and ACP here acts as a leaving group. The ACP in the acetyl side departed with a pair of electrons. So this is a Claisen condensation, and this forms a carbon-carbon bond, and this bond formed is exactly one of these bonds highlighted in purple in the fatty acid above. It's possible to iterate this process through a means that we'll see on the next slide. First, let's look a little bit more at the mechanism of this Claisen-type condensation. Decarboxylation can occur inside the active site of the enzyme with protonation of the leaving group. And notice here that this resembles the decarboxylation that we saw in the malonic and acetoacetic ester syntheses, in that the leaving group is an enol. This electron flow forms an enol intermediate. And at this point, the electrophilic acetyl ACP comes in, and now we have a nucleophilic enol in the presence of an electrophilic thioester, and here the classic Claisen sort of acylation can take place. And so the nucleophile adds in, the ACP leaving group departs, so on and so forth. So I won't show all of the electron flow in detail, I'll just note that this is essentially the acylation mechanism we've already seen. Nucleophilic addition followed by beta elimination of a leaving group, probably in an enzymatic or biochemical context with some proton transfers to avoid very unstable negative and positively charged reactive intermediates. And this is how we get the 1,3-dicarbonyl product. But to get to the fatty acid, if we back up to this slide, notice we need to reduce that carbon down to a CH2 group. While leaving the carboxylic acid group intact. How would we do this in the laboratory? This is actually worth pausing the video and thinking about for a second to think about how you would synthesize this product from this starting material. How would you convert this ketone into a CH2 group? Doing this without messing with the ester or the carbonyl ACP group is a little bit tricky. How I would think about it is first reducing with something like sodium borohydride the ketone selectively to a hydroxyl group, and then we can think about a dehydration here with something like H2SO4, protonate the OH oxygen, water departs, then we lose a proton to get this alpha-beta unsaturated carbonyl ACP. And then we can imagine reducing the CC double bond using something like H2 and palladium to get to the saturated ACP. And so we have kind of a reduction to the beta hydroxy carbonyl ACP, dehydration, followed by a second reduction of the CC double bond. And in fact, this is very similar to how nature does it. Nature does this by first reducing the ketone group, not with sodium borohydride, which is uncalled for in a biochemical context, but with NADPH and H+. This reduces that CO double bond to an alcohol, and then water is lost, and this is an enzyme-catalyzed dehydration reaction. And then NADPH reduces again the CC double bond in the active site of an enzyme to give now the saturated carbonyl ACP product. And 3 enzymes are involved in this. 3-ketoacyl ACP reductase is what accomplishes this first reduction. 3-hydroxyacyl ACP dehydratase accomplishes the dehydration that we're seeing right here, and then enoyl ACP reductase accomplishes this reduction of now the enoyl ACP, right? Enoyl referring to the ene and oil groups built into this substrate. And now notice we have a alkanoyl ACP, we might say, that's ready for another round of Claisen condensation as an electrophile, right? So another molecule of malonyl-CoA can come in. We will lose another equivalent of carbon dioxide here. The enol of the malonyl ACP forms, and that reacts with the longer chain carbonyl ACP to give a new bond via Claisen condensation. And then the cycle repeats over and over and over again after the 3 steps outlined at the top of this slide. So the biosynthesis of fatty acids follows a path involving Claisen condensation for that key carbon-carbon bond formation, and then actually a biosynthetic path that mirrors what we would think about doing in the laboratory through something like this. An example of nature and the laboratory sort of being in resonance or in harmony, if you will. This figure shows the overarching idea with the Claisen condensation of malonyl ACP with that growing carbonyl ACP chain here kind of on the right, and then the cycle of reduction, dehydration, and reduction again to elongate the chain and generate a long chain of CH2 groups. And a point I want to make on this slide is that the structure, the overall structure of this biosynthetic pathway is dictated by and can be understood through fundamental principles and ideas about organic chemistry. For example, we can use redox logic, looking for oxidation and reduction processes. And we can think about alternatives and understand and begin to reason through why alternatives actually don't take place. A simpler reaction that would seem to give the same result as what we've shown here is just a Claisen condensation of acetyl coenzyme A directly. Why can't we form, for example, the enol of acetyl coenzyme A and have that react with another molecule of acetyl coenzyme A directly? A hint is provided by the fact that this equilibrium favors the keto side profoundly, right? The keto side is profoundly favored because enols are generally less stable than the corresponding keto tautomers, right? Fundamental ideas about tautomerization there. But when there's a carboxyl group connected to the alpha carbon, now forming the enol doesn't involve deprotonation. It involves loss of CO2, which is a gas. So that can easily separate itself, and in fact will separate itself from the malonyl ACP, and the enol can now be formed not unfavorably, but quite favorably as CO2 departs. And this is exactly what drives enolization in the condensation process. So having the CO2 minus group there is actually critical for driving this process forward. It's the loss of CO2. You can even think about it as the exhalation of CO2 from your body is helping to drive fatty acid biosynthesis.